reminding you of some example of local mirror symmetry that we understand fairly well, and that's C2 minus the complement of the conic. So the reason this example is interesting is because, so I will explain how mirror symmetry works for it, but if you think from the SYZ point of view, it corresponds to something like an affine chart with one singularity, and then the monodromy around the singularity is given by this kind of basic transformation. So another way to think about it is that if you wanted to understand mirror symmetry for K3 surfaces, which are fibers and fibered and Lagrangian tori, then what you would do is you would understand mirror symmetry for 24 of these charts, and then you would try to glue them together, and then you would see, well, that the gluing is somehow quite a non-trivial procedure, and then you would go through this wall-crossing story of concentric Sogelman and so on. But still, this would be your starting ingredient. And so this example, so you want to have kind of as good a handle as possible how to go from this as a symplectic manifold to this as some kind of SYZ feature. And so this story was developed by many people, but I came into it with joint work with Uru and Katsarkov. And the reason I want to talk about this work is because this is the perspective which I will then build upon. So the perspective we take is that we take this space, and I actually have some kind of notes, amazingly enough. So this is supposed to be, well, anyway, let's just call it X for now. So we take this space X, and then we project it to C, okay, and via the map X1, X2. So let me now draw a picture. So this picture is not going to be the same. So this is kind of a SYZ picture. This picture is going to be, instead, that I draw like that. This is plane C. This is the fiber at 1, which we remove. This is the fiber at 0, which has this kind of standard singularity. And the general fiber is a smooth conic. Good. So now I want to explain how to start with this picture and construct a nice family of Lagrangians, which then gives us this picture. And then that family will be so nice that we'll be able to understand mirror symmetry for it and basically understand that this space is self-mirror. The point that we're heading towards, X is self. Okay, so how do I proceed? First, I think about, let's say that I've understood mirror symmetry for the fiber. That's very easy to understand. The smooth fiber is just this conic, so it has this family of Lagrangian circles. And if you look at the space of local systems, rank 1 local systems, then you again get a copy of C star. So I take this, and then I work locally. So I'm going to work in the fiber and the base. In the base, I do something similar. So over here, this is a puncture. So again, I can draw a circle. Okay? And if I take the circle and I take the circle in the fiber, I can parallel transport the circle to obtain a Lagrangian torus. So there's one Lagrangian torus, or one family of Lagrangian tori that I get by going around this singularity, just this puncture. But there's also a family of Lagrangian tori that I get by going around both the puncture and the critical point. And the fact that there are these two families of Lagrangian tori tells me that, these have names. Sorry, I should have used different colors, I apologize. So the green one, the green Lagrangian torus, I'm going to call, because of some symplectic topology, I'm going to call it the Clifford. Okay? And the red one, I'm going to call it Chekhanov. And this picture is not completely right so this picture is right when we try to do SYZ fibrations, but later it'll be useful to kind of deform Clifford and Chekhanov to make them intersect. But anyway, so the Clifford and Chikhanov tori give two C star squared charts for the mirror. And so the idea is the mirror is obtained by gluing them together. But if you glue them together, gluing these charts does not give x, does not get x, which is C2 minus x1, x2 equals 1. By the way, these charts, if you think about them from this point of view here, they correspond to x1 not equal to 0 and x2 not equal to 0. Those are the two possible charts. There, you don't get the whole space. You are missing one point. We're missing the origin. And I think this place where this was first worked out is some explicitly some notes of Seibel. You can recover the origin. So what we did is we built an SYZ vibration, observed there is a singular fiber. So in this language, Seibel says you can recover the origin by adding the immersed Lagrangian, S2, which corresponds to let me just now draw it again, which corresponds to this picture, and not the same picture as before. But now instead of taking a circle that goes around just this one puncture, or taking a circle that goes around the puncture and the singularity, I take a circle that goes through the singularity. Okay? And then the fiber I parallel transport the vanishing side. So you just have to be a little bit careful. There's like two stories taking place. On the one hand, there's a story which is constructing an SYZ vibration, okay, which is what was done here. And you should imagine constructing SYZ vibration is what you need to do in order to understand Floer theory over the Nobby covering, in order to be able to do something which later has a good chance of generalizing, of being able to be like just the local input of some computation for a closed symplectic manifold. But then there's also just trying to understand the local, some kind of wrapped Fukaya category of X or some kind of category of exact Lagrangian. And from that point of view, it's better to just say there's only 3 Lagrangians involved in this story: Clifford Lagrangian, a Chikhanov Lagrangian, and that immersed Lagrangian. Okay, so the goal of this lecture is to basically explain how to do this in higher dimensions. Goal, how to do this for, really, I want to say kind of for the analog in higher dimensions, but what I want to say is I want to do it for all the singularities that appear in this gross Z-Bird program, but I'm just going to say for higher dimensions. And just to indicate the difficulty, the difficulty is going to be that the analog of this construction does not give an immersed Lagrangian, it gives something with worse singularities. Bad singularities. E.g., if you now work with C3 minus the locus where x1, x2, x3 equals 1, and you do the same construction, yields a Lagrangian which yields a Lagrangian which is locally a cone on a 2 torus. In fact, more precisely, it looks like a double cone on a 2 torus. Something like that. Because, roughly speaking, here the vanishing cycle is a circle. Okay? So you just collapse a circle to a point. That's what gives you a disk. Now you collapse it both on this side and on this side. But if you do the same thing in higher dimensions, the vanishing cycle is going to be a 2 torus. And so you bring it here, and you get a 2 torus being pinched to a point. That's singular. You bring in the other side, it's another 2 torus being pinched to a point. And so this kind of object is the kind of object for which we do not know how to do Floer theory. And I just want to argue that in some sense, maybe we don't want to learn how to do Floer theory. It just may be too hard. Okay? And if we can do things some other way, then we might as well do this. So the slogan is to trade singularities for holomorphic disks. So that's a really badly singular Lagrangian. It's going to get worse as the dimension goes up. And instead, what I want to do is I want to just find an immersed Lagrangian, which lives locally near that singular Lagrangian. And that immersed Lagrangian might bound some holomorphic disks, and so that might make our life a little bit complicated. But this is something we can handle. Holomorphic disk bounded by immersed Lagrangians. And the key ingredient is to basically, is to replace that circle that goes from through the singularity by a circle that winds around somehow twice and avoids the singularity. So, you really want to say kind of use a variant of Seidel's immersed Lagrangian in the pair of pants. So the way that Paul usually draws his Lagrangian goes somewhat, I can just remember. There you go. Okay. So he draws some Lagrangian like this, except for us, our pair of pants, where our pair of pants is going to be, one part of the pair of pants is infinity, which is infinity. The other one is this critical point x here, and the third one is this puncture, which is actually later not going to be a puncture here. Okay, but the way I draw it, it doesn't end up looking like this. I like to call it the yin-yang Lagrangian. So let me draw it for you, because some things I feel like slightly more apparent. So let me draw it. So we're going to always have two singularities, something like this, something like this. And then the Lagrangian that I want to draw will look like this. Okay, and now I have to. Okay. So that's, and this is Paul's thing. Okay, it's the same Lagrangian, but drawn differently. And as I said, I think some things will be more apparent from this. Good. So how should you think about this? What you should think about this is that I took 2 copies of this guy. The idea is that we take 2 copies of this, okay, which are basically, imagine kind of squishing all of these here, and then you do some kind of surgery to them. Then you do some kind of surgery there, and that gives rise to this. Okay. So one talk I could give, and maybe that's not the one I give, is I basically explain how this story. Maybe I'll start with that. Maybe that would be nice. How the story works first. But it turns out that this story works in kind of some far larger generality. But let's just start with that. So let's consider the case, as I was illustrating earlier, of C3 with potential XYZ. Okay. So what does this picture tell you? Well, this picture tells you should take this Lagrangian, and you should take, so again, just to be clear, the fiber is the locus, the general fiber is the locus where x1, x2, x3 equals lambda not equal to 0. This is a copy of C star squared. You can invert any of the variables. if you impose a condition on the norm, then you get a Lagrangian torus. And if you make the norms basically essentially equal, then you get an actual vanishing cycle from this. That's a little bit of a lie because the most natural way to put that is at 1, but it's not configurable. Great. So now what I want to explain is how does the mirror equation arise? Okay. So the claim in this case, essentially, so the key statement of mirror symmetry in this situation, the mirror symmetry amounts to, I mean, you could do many things. You could talk about like how solution moduli spaces can be glued together. But the key thing that's going to happen is there's going to be, if you do things using the tori that I talked before, the kind of Chekhanov and Clifford configurations, the circles that don't go through the singularity, you will see that there is a locus of the mirror that's missing. Okay? And that should be encoded by, should be kind of known by this inverse Lagrangian. So mirror symmetry amounts to, this is a little bit of an exaggeration, but to the statement that the space of simple object, whatever that means, I don't want to be too precise about it, objects of the Sakai category supported on this immersed torus okay? This space of simple objects of the Sakai category supporting this torus is a copy of the curve given by the equation 1 plus y1 plus y2 sitting inside C star squared. Okay. Why does mirror symmetry amount to this? Because if you did the naive thing, and again, as I'll repeat again, if you took the Clifford and the Chekhanov configurations, you would get everything else of the expected mirror. By the way, the mirror is supposed to be the total space of the conic bundle over this, but then there's going to be the locus, the set of x1, x2 equals 1 plus y1 plus y2, 2, sitting inside C2 with x coordinates, cross C star 2 with y coordinates. And what I'm telling you is, if you look at the Clifford and the Chekhanov configurations, respectively correspond to where x1 is not 0 and x2 is not 0. Okay? But then there is a locus where x1 and x2 are both 0, and you cannot get those from just the obvious tori that we had before. You need something else. And if you were following this philosophy, you would say the thing that you need is this bad singular Lagrangian, which has this double cone on the two torus. But you don't want to do that. And so the statement basically is, this does the job. And it gives us all the points that we're looking for. Okay? So let me see what time it is. Okay? So I could basically prove this. But really what I want to explain is just where does this equation come from? Okay? Where does this equation come from? So the space of local system, the space of basically the space of objects that's supported on this, you should imagine is like the space of local systems on this three torus. We start with H1 of T3 having rank 3. Okay? And what I want to do is I want to associate to that a torus with a complex torus with coordinates y0, y1, and y2. So what is y0? Y0 measures the monodromy of my local system in the base. And these two are in the fiber. The H1 corresponds to rank 1 local systems. So they wind around the base and wind around the fiber. And now, the first claim is that, in fact, if you have an object of the Fukaya category, then y0 must equal 1. Each object of the Fukaya category we have y0 equals 1. Okay? So this is some equation, if you know the Fukaya category, you have to remember that not every Lagrangian gives you an object of the Fukaya category. Some Lagrangians give you objects which are obstructed. Okay? There's non-trivial curvature. This is the statement that the curvature is non-trivial. How do I see that? Yeah, how do I see that? Well, I look at this picture and I try to think about what are the holomorphic disks that this Lagrangian bounds. Well, actually, this Lagrangian bounds no holomorphic disks. Okay, but then you remember it's an immersed Lagrangian. So the correct question to ask is, what are the holomorphic disks with possibly one corner that this Lagrangian bounds? Okay, and the answer is there are 2 families of them. In fact, it will turn out that there are 6 families of them, but at least from the point of view of the base, it looks like there's 2 families of them. And they correspond to things which project to either this lobe or the symmetric one. And if you were to try to count these holomorphic disks, you would get a non-trivial contribution at the generator of Floer cohomology that corresponds to this self-intersection. And the only way for you to get curvature is for these contributions to cancel. But then clearly, this one winds around this, and this one winds around the rest of the curve. Okay? So if the contributions are going to cancel, you better have some cancellation property of the weights better be equal. And that's exactly what y0 equals 1 tells you. Y0 equals 1 tells you that if you trivialize it over this half, then on the other half you don't get any monotropy. So curvature equals 0.
So did you say 6 because they link to 3 disks?
That's right, I'll say that in a moment. That's required to get the next part. So 0. So the so the equation rises from needing the contribution, needing to get cancellation. For the contributions of the 2 lobes. Okay. And again, just to be clear, if whatever this y0 is, the curvature is going to be something like 1 minus y0 times something. So you need to get this. You need to get this. Okay? So that is the first part. But we're not interested in the moduli space of objects. We're interested in the moduli space of objects which have non-zero Floer homology, because if they vanish, that's not good for us either. So next,
Sorry, non-zero Floer homology endomorphisms or?
Non-zero Floer homology, yeah, endomorphism.
Endomorphism.
Yeah. And then you can do it in several ways, but next we need to get HM star of this Lagrangian equipped with the corresponding local system. To not vanish. And what does it mean for it to not vanish? It just means that the identity doesn't vanish. That's all you need. I.e., unit is not in the image of the differential. Okay, and now you think about what could possibly kill the unit. What is the unit? The unit is, you pick a generic point, and you try to see, is there a holomorphic curve that kind of passes through a generic point? It turns out that's exactly what these lobes are measuring. We pick a generic point. Ask about the number of, well, again, there's no disks, but there are these kind of disks with one corner. Passing through that point. And now I think Marco made the remark, basically, so I have to pick it on this, either on the boundary of this green lobe or the red lobe. It doesn't make a difference. I mean, the curvature is, in fact, the curvature is zero is the reason that it doesn't make a difference. So you pick it on one of these, let's say on this one. And then you are really asking about what are the lifts of this green disk in the base to the total space. Ask about lifts of each lobe, or one of the lobes, to the total space. And this is now some kind of standard thing that we know how to do. What you do...
These are all master index to, well, I'm not sure how to say this.
That's right. So, I
mean, there's a two...
That's right. There is a two parameter. If you fix this point, then there will be exactly one of them. So there will must not two. Yes, index of 2. Then you have to decide how to assign an index because it has a core variable. So, to the total space. So this is something we now know how to do, and the way basically you do it is there's only one singularity. Outside of this singularity, everything is tripped up. So you look at this singularity, and you realize that this singularity has 3 components. Okay, singular fiber has 3 components. And that, in fact, tells you that the kind of relative H2, it's not quite a relative H2 because this thing is inverse, so you have to think very carefully what you mean by relative H2. But since I won't write it as a formula, relative H2 has 2 possible classes, has 3 possible classes that are detected by the intersection number with that fiber. I'm going to keep this picture. Okay, so the picture again is here. That's basically what the fiber over this looks like. And now you can take this green disk. You can pick a section over it that goes through here, or through here, or through here. Okay. And if you do the relative H2 computation, then you can get there's a boundary homomorphism to a relative H1, and you see that that map does the right thing, and in particular that the contributions of the one of the section, if you fix a base section, then one of them winds once around one direction in the fiber, and the other one winds the other direction. So if we fix a section, one, the other two wind around y1 and y2. And if you go through this, what that tells you is that the formula for the differential of the thing that could hit the unit, so the differential basically is 1 plus y1 plus y2, which is what I promised you as the equation for the mirror.
When you said it's not really the relative H2, you mean that you're looking at the map from the normalization to
Yeah,
the
that's right.
space,
That's
and,
exactly
and
right.
you're doing
That's
some
exactly
kind of a relative.
I mean, it's really, that's the problem. The problem is that
It's a cone. It's a cone.
let me say it like
correct
this.
map.
You fix this intersection point, and now you look at the space of things with one corner. That's the point. It's not about the normalization. You have to put in this corner here.
Corner in the source disk.
Yeah, corner in the source disk, such that which actually branch here. And when you actually branch here, you see, well, the three possible sections of this, that's some kind of relative H2, and that has the three classes that we're looking for. And there's a little bit of normalization that has to be done, but exactly because what Paul said, like when you have corners, then saying that something has a given Maslov index requires a little bit more care. So, but it literally is because of the intersections, and clearly you can't change the intersections by moving clearly the intersections are Homotype invariants in this situation. Okay, so what I've explained now is how this equation, which is, we all know is the equation mirror of C3 or something like that, arises by considering this Lagrangian. Okay? And just to recapitulate, if you want to do something, the simplest thing you could do to tell yourself, the simplest thing you could do to tell yourself that you have proved homological mirror symmetry is to just compute the chi category and check that it matches up. Okay? So let me just say that. So just proofs of HNS in increasing levels of difficulty. One, identify the wrapped Floer cohomology of the, I'm going to say, positive real locus with the ring of functions on the mirror. Okay? In this case, if you draw a picture like this positive real locus ends up basically projecting to some arc like this. Okay? But literally, x1 and x2 are both positive, and we also need this condition that the norm is greater than 1. So you have to be, that's why I put it in quotes. It's this Lagrangian here, Lagrangian R3. Okay? You can compute, using what we know now about the monodromy of this. We know about the monodromy of this situation. It's not hard to actually compute the Floer cohomology, but identify it as a ring with the ring of functions of the mirror. It's all supported in degree 0. Okay? Therefore, there isn't much thinking about A infinity structure you have to do. There's no thinking about A infinity structure. Just the ring structure gives you everything. And now, with this technology of Ganatra, you can basically conclude that it generates its own summand of the Floer category. So automatic generation. Although I think, I told Shield that he should just write the version for the Floer category, and he didn't. But anyway, so automatic generation implies that this generates a type. Generates a summand, and then you can just check that that summand must be everything. Okay, this is what I think is somehow the easiest thing. This approach, my philosophy is we do this and then we use this to bootstrap to make our life easier when we have to do other computations. But this approach has the disadvantage that if you want to think of this as like a local picture of something bigger, then it's really hard to say take this Lagrangian here and make it be some a local piece of something bigger because it goes out to infinity. So approach number 2 is you look at the space of objects which are supported on exact Lagrangians.
So,
yes?
when you say this sentence, do you mean you fix the Lagrangian and then you look at all local systems such that the brain has no trivial cohomology?
Here?
Yeah.
Yeah, and in fact, a little bit vaguer than that, because really what I like to say is you want to look at simple objects, and to identify what we mean by simple objects, you really need to have done this first. I really want the space of Lagrangians whose Floer homology with this generator has rank 1. That's the simplest thing. then I don't have to think too much about what I mean. But in practice, there's some kind of specific geometry that I have in mind. Supported on exact Lagrangian inversions. Oh, I forgot to say, this thing, if you think about it appropriately, is an exact Lagrangian immersion when the green and the red part have the same area. Okay? That makes life reasonable, makes it possible for us to do Floer theory without too much of a headache. Lagrangian immersion. And this is what, I referred earlier to some notes of Seidel about the two-dimensional case. That's what he wrote up in dimension 2. N equals 2. And then this is what I'm explaining now for n equals 3 for one direction. I just explained. Okay, and then there is the real deal, what I consider the real deal, okay, which is basically to drop this exact condition. Okay? And that makes life much harder, but my point of view is that that's the way that we kind of really need to do things in order to be able to kind of work with eventually work with closed symplectic manifolds. Drop the exact condition. Okay, so I'm not going to talk about 3. I'm just basically going to say that for part 2, now this picture that I explained works for part 2, not just for this guy, but also for many more. Okay, questions? So instead of doing many more singularities, let me instead do the other one, because the other one in dimension 3. That one's very interesting because there's so many approaches to it. And so for a long time, what I was really trying to look for is an approach that would work in exactly the same way for this side, for this one singularity, and for the other side. So I already wrote the equation. So let's try this. Let's try our strategy. Let's try our strategy on now the symplectic manifold X, which we were going to set to be, I wrote the equation earlier, but I'll do it again. X1, X2 equals 1 plus Y1 plus Y2 inside C2X plus C2Y. And again, there are many, many things one could do with this. There's
C star.
C star, thank you. Many things one could do, but I want something that looks as close to this as possible for some reasons which maybe will be apparent at the very end when I say, now this is the class of singularities. So in particular, what I want to do is I want to start with a projection back from this to C, which is given by either of these two expressions. Okay. Let's say x1, x2. So now let's analyze what happens. Well, this function only has critical points at 0. That hasn't changed. So there's still a critical point there. Sorry. And the fiber, maybe I should. I don't quite do that. Okay, anyway, so this function here, 1 plus y1 plus y2, that has no critical points. However, because we're working in C star squared, there's actually a special value. So what I'm going to do now is I'm going to tell you what the fibers are. So the special value of this function function y1 plus y2 is special. Look, if you set y1 equals minus y2 in C star squared, the solution that you get is a cylinder. But on the other hand, if you do lambda plus y1 plus y2, and lambda is not 0, then instead you get a pair of pants. So here the fiber is a cylinder across another cylinder. Generically, the fiber is a cylinder across a pair of pants. And here, the fiber is a standard singularity dimension 2 crossed with a pair of pants. Okay? So it's the same thing as before. And the only difference is before we punctured here. We removed this fiber. But if you write this equation, you don't remove this fiber. Right? We're not going to remove this fiber. We're going to keep the same fiber. We're going to keep the whole entire fiber. We're going to take it inside C star squared. Let me just now observe Just, you might think, why did we puncture before but not now? So let me just observe something, which is that the complement of that fiber, remark, C3 minus the locus where x1, x2, x3 equals 1 is the same as the subset of C3 cross C star, where you write the equation x1 plus x2 plus, x1 times x2 times x3 equals 1 plus. Okay, this is complete tautology, but this is just an explanation for why in this dimension we remove the fiber, and in this dimension we don't remove the fiber. Instead we pick up the singularity. Okay, I haven't said anything deep, but I'm just telling you this and this, they fit in the same framework. Good. So now we do the same thing as before. So we say we understand mirror symmetry for the pair of pants. We know what we are supposed to do. So start with Lagrangians in the pair of pants. Well, really in the general fiber, the smooth fiber, which is across this. Okay. And there are, so what I want to do, I want to start with the simplest story possible. So my simplest story possible is going to do everything exact. And I'm going to take this Lagrangian, and then I'm going to take, okay, so now I'm going to draw a picture which is somehow mathematically incorrect, but it's, you can just imagine what I do correctly. Okay. You could draw this Lagrangian, or, that's one possibility. And the other possibility, let's do a different color, is that you take, take this one, still the same, and now you do this one. Okay, so if I do this, you should ask me, what about the third circle, the one that goes around this puncture? Let me come back to that in a second. What am I going to do with these Lagrangians, these Lagrangian tori? So what I want to do is I want to focus on this idea of first building C star cube charts. Okay, they're like some kind of cluster charts or something like that. C star cube charts. They may not cover everything, but we'll worry about what's missing later. So using these Lagrangian tori in the fiber. And the Clifford and Chichanov tori in the base, Chichanov circles in the base, we get 4 Lagrangian tori, embedded Lagrangian 3 tori in our space. If there's any questions, I can. No. And now the claim is that these 4 Lagrangian tori give us our charts for the mirror space. But if you know what the mirror space is, charts, anyway, for a big open part, for the complement of the codimension 2 parts, for mirror. But actually, the mirror space is, again, is the one that we had before. This is kind of C3 minus x1, x2, x3 equals. Okay. 1. 1. Thank you. So, but if you know this story, you know that actually this space has a cover by 3 tori, not 4. So we have 1 too many. Okay. So that's what I want to explain, what that 1 too many is, and then when I do that, I'll also be able to simultaneously explain what happens with the other 2 charts which you might have tried to build. So, so the problem occurs on the Chichanov side. So the observation I would say this observation kind of, was explained to me by Isaac Silva. This is kind of the best way to explain it, is that if you look at this picture, okay, and you draw this Chekhanov torus here, okay, then because you haven't picked up this other singularity, this region here, so this is just a copy of the fiber, this is a copy of the cylinder, crossed with C star squared. It's not quite exactly it, but it embeds in it, and it's basically the right piece. So if you take if we do our construction here, where these need names, I'm sorry. So let's call this L1, and let's call this L2. So the key claim is that the 3 tori obtained from L1 and L2 by this construction are just the standard tori in this copy of C star cube.
They're all the same.
They're both the same. L1 and L2 are the same. They're Hamiltonian isotopic if you make them exact. Okay. So the parallel transport of L1 and L2 by Chekhanov circle are Hamiltonian isotopic. i.e., it's the same chart. Nothing changes. Now that we're here, I can explain to you what would happen if instead of parallel transporting those things, I instead parallel transported this picture. What if I instead parallel transport? And if you do that, you basically, and you do it carefully enough, you realize there is no way to make this thing exact. So you cannot make this thing exact. And the reason you know that it cannot be exact is because it bounds a homomorphic disk. The homomorphic disk. Disk. And the holomorphic disk, roughly speaking, just fills out this plane. Okay? It just fills out this disk. So this configuration is yes.
So the way that this third one is distinguished is because as you go into the fiber with the little square, the two other circles collide.
That's right. So the way I actually think about it is that this gets pushed down to minus infinity. So so indeed. So Paul is saying that this fiber, remember, this fiber here is a cylinder across a cylinder. And what you should basically imagine is that this cylinder here is like this end. This cylinder is like this end. And in the topology of what happens when you go from here to that singularity is that this handle gets pushed down to minus infinity. But the stuff that stays up here just gets filled in, and so then you see this holomorphic disk that lives over here that tells you that this other Lagrangian, remember here we constructed 4 charts, and naively maybe you were supposed to get 6, but 2 of them just don't make sense. 2 of them don't make sense. So now, so the claim now is that this parallel transport gives you two Hamiltonian isotopic tori. However, if you do the same thing on the Clifford side, then it's just not true. And you can prove that it's not true because you see a non-trivial wall crossing when you try to glue the spaces by equivalence. The corresponding Clifford tori are distinct by a wall crossing computation. And so if you go through this, the outcome is that we have 3 charts for C3 minus the locus where x1, x2, x3 equals 0. And at this stage, I decide to change my labeling and call this x0, x1, x2. Okay, I apologize for that. These are 3 charts, and these are given by x. Sorry, I need to figure out exactly how to say this. x1 and x2 not equal to 0, and this is this kind of Chekhanov side. And then the other ones are the 2 tori, 2, 3 tori obtained on the Clifford side. If you do this construction, then you realize that you are missing some pieces. You're basically missing the coordinate hyperplanes. The coordinate lines. You're missing the coordinate lines. How to get the coordinate lines back? Via the same procedure that we discussed, or that I kind of explained earlier. So, missing coordinate lines. And so to get them back, so you need, 1, you need to do the parallel transport of Seidel's Lagrangian in the fiber on the Clifford side. That's the first thing you need to do. Clifford transport of, let me just draw a picture instead of giving things names. Times this. That's one coordinate line. And 2, you need this yin-yang, which again is again a version of this yin-yang construction of the base applied to these 2 different tori. Parallel transport. Applied to L0 and L1, L1 and L2. And if you do this, then you get the coordinate lines minus 1 point, which is the origin. And if you, then how do you get it back? You take this thing in the fiber and you parallel transport it. Okay, that completes this. Okay, so in the last 5 minutes, I just want to say what this generalizes to. So this, you know, the rest, last 5 minutes are basically kind of, these things must be true, but I have not sat down to prove them. So what I want to do is I want to introduce a symplectic manifold. Let's call it X and N, which is the set of points satisfying the equation that the product from I equals 0 to M of some coordinates xi equals 1 plus the sum of some coordinates yj, and j goes from 1 to n. And this is supposed to live inside Cm plus 1 cross C star to the end. So what have I done? I basically combined one of the singularities with the other singularities by some kind of twisting product. Okay? So the claim, as far as I understand, even though I haven't sat down and do the computations, that all the singularities that appear in the gross zebra program are given by these quotients and covers. So how do I want to analyze it? I want to analyze it exactly like I explained to you for dimension 2 and dimension 3. This maps down to C via either this product or the sum. And there are, as always, 2 singular fibers. There's one singular fiber at 0, which is basically product xi equals 0. Okay, that's clearly singular. And then something which really you should think of as like a singularity at infinity. I'll just say it like that, singularity at infinity over 1 sum yi equals 0. these Lagrangians pretty. We understand that the fiber is the pair of pants, is the product of C star to the M with the pair of pants. And we'll just call it Hn minus 1. This is going to be a set of sum of yi minus 1. Okay? That's a smooth fiber. Now, inside this fiber, there are some Lagrangian tori. So this, let me just draw the next dimension. Next dimension, drawing this tropical thing. Anyway, no, I don't want to draw the rest. So there are plenty of Lagrangian tori floating around. There's one for each facet of this tropical hypersurface. But what you want to do is you want to focus on the ones which correspond to one of the coordinates being very small. So for each. And you get the Lagrangian torus in Hn minus 1, which is analogous to the circles at the two ends of the curve. And now there's a question of, you take this thing here, you need to actually make it exact in order for the construction to go through. That's kind of one of the difficulties. So anyway, so you take this Lagrangian torus, and you take the product with the standard torus Tm inside C star Tm. And from this, you get n plus 1. So you get, n charts for C star to the n cross C star to the m charts for the mirror space from the Clifford side, and one chart from the Chicano side. Just like before, because if you do things on the Chicano side, it turns out it doesn't matter whether you do this and do parallel transport or do this parallel transport, they are actually isomorphic. And so this, then you glue together, and by wall crossing, and you get a complement of codimension 2 part of the mirror space, which the reason I chose that terminology is because it's just x and you just swap n and n. You swap the thing over which you've taken the product and the thing over which you've taken the sum. So anyway, so this gives a strategy which is somehow uniform in dimension and uniform in the equation of the toric equation of the singularity for handling kind of local mirror symmetry via immersed Lagrangians. Okay, I will stop here.
Questions?
Yeah.
It eventually gives proof of homological mirror symmetry and gross Hilbert framework.
Well, eventually. Are you asking me, is that what I'm aiming for? Yes. I'm aiming for this to be one ingredient of proving homological mirror symmetry in the gross Hilbert framework via a local to global approach. There are probably going to be other approaches which are more directly global using line models. This is just locally, it's right. Okay? Then you patch together these charts, and then, so I recently proved that if you don't have singularities, then this kind of patching gives you fully faithful embedding. So then that would be the goal. You just do the same thing with these singularities, and you get a fully faithful embedding of the Fukaya category of this big space with these singularities into some category of coherent sheaves and some rigid analytic space. And then you have to figure out what is the what is the, no, the image is fine, it's not going to be that hard. If you have enough Lagrangian sections, you'll check that the image contains generator. No, the hard part is to figure out what the mirror map is. This procedure is really bad for figuring out what the mirror map is. It just says, there's the mirror map. But anyway, one thing at a time.
So there was a 0.3 drop exactness at some point.
No, I didn't mean to drop exactness. You should imagine that I'm just in this talk text, I want to stick with exactness. You can draw all the pictures that I drew, you can just arrange them so that they correspond to exact things.
At some point you excluded a 3 torus.
Yeah, I said this 3 torus does not fit in our picture because you can't make it exact. You don't want to think about it. In fact, you just cannot make it exact for much better reasons than what it's not in a class where you can make the area zero. Anyway, I excluded that one from consideration so that we would only think about exact ones.
Any more questions? Let's thank Mohammed again.